skimmed the tip of the iceberg, but I'm looking forward. It's good to be a little surprised, you know.
It was a nice pun.
Yeah. Well, it's one that I use often because it's applicable widely.
Nice. Are we recording? Sweet. Okay, cool. Thanks for coming on. I appreciate it. Sorry for the kind of wacky getting lost and having you walk through the heat.
But thanks for having me. It's fine. It's always fun to explore a new part of campus that I haven't been to before.
Yeah. This is a nice part of campus. The view's really cool, and you don't get a lot of views like this.
I noticed the same thing when I walked in. I can't imagine having a class in here. It's quite distracting, but I guess you get used to it.
I actually had a class in here a while back.
Is that how you found out about this room?
Yeah,
nice.
That's exactly how I found out. And then I kind of scouted it out. I was like, does anyone use this during the summer? It doesn't look like it. So, no one uses it during the summer.
Very nice.
Yeah. How's your research going? How you doing?
Yeah, it's going well. Summer is a fun time because it's a little bit less structured. So I go through sort of phases of having a lot of time to do research, which is nice, but then there's also sort of busy times that get scheduled. So I just got back from teaching at a summer school in Italy, in northern Italy, about glaciers in the climate system, which is really fun. We had one PhD student from UT was there, and then 35 other students from around the world and 9 instructors, and we just are staying in the Alps and talking about glaciers all day, every day for about 2 weeks, which is really a treat to get to do. And then I was traveling for some other work-related things, so I'm just kind of getting back and getting settled and getting into the rhythm of the summer. But yeah, it's going well.
You gotta let me know how I can sign up for that after
if
this
you
podcast.
decide to do a PhD, then I will give you the info.
Sweet. Okay. So let's start out with just like basic, just sort of introductory. Why is studying ice sheet dynamics in regard to climate change important?
Well, ice sheets are a really critical and fragile part of the climate system. One of the ways that we recognize the impacts of climate change already ongoing is in the impact that warming temperatures have had on glaciers around the world. Many small glaciers have retreated kilometers, tens of kilometers, in response to warming since the early 1900s. And these are features that when they disappear, we lose access to water resources, we lose habitats, we lose a kind of natural feature that is very spectacular and not unique to our planet, but certainly remarkable about our planet. As the glaciers have continued to melt, we've also seen, in the last 30 years, a response from the big ice sheets as well. And the threat there is that the ice sheets today on Earth, in Antarctica and Greenland, if they were to melt completely, it would raise global sea level by about 230 feet, which is a huge amount that would displace a sizable proportion of the global population. I think it's something like, I'll get this wrong, but 1 billion people live within 100 kilometers of the coastline or something like that. So even small changes in sea level, particularly in coasts that have relatively low relief, can displace a lot of people. And so when we think about the kinds of impacts that we expect from climate change in the coming centuries, ice sheets are really central to that.
And have we always had ice at our poles, or like how recent in geologic time are these big ice sheets?
Yeah, that's a great question, and that is something that is really at the heart of my research. I'm interested in, we know that the ice sheets are changing today and responding to climate. I'm interested in looking to periods in the past when the ice sheets were also changing to try to understand how quickly that happened, what drove that, and what that might teach us about ice sheet stability more broadly. In Antarctica, there's been some kind of ice sheet for the last 34 million years. That ice sheet in the Antarctic ice sheet holds something like 60 meters, 180 feet of sea level equivalent if it were to melt completely. And so about 34 million years ago, we think an ice cap expanded rapidly in Antarctica and has been waxing and waning, fluctuating in response to changes in its local environment and also changes in Earth's climate ever since then. In the northern hemisphere, the story is a bit more complicated. We've had more or less continuous ice cover for the last 3 million years or so, but there was certainly ephemeral ice before that, and there have also been pretty big changes in the amount of ice cover in the northern hemisphere over the last 3 million years, from ice sheets that were smaller than today, so warm periods in the last few 100,000 years when the Greenland ice sheet was substantially smaller than it is today, but also to cold periods like the last glacial maximum when most of northern North America was covered by an ice sheet and global sea level fell by something like 400 feet because of the changes in ice volume, mostly in the northern hemisphere. So we've had ice for millions of years, but what we know from the geologic record is that ice has changed a lot. And that's why looking to the geologic record to understand how ice sheet changes is such a rich opportunity for helping us contextualize the changes we see today.
And tell me why we have these sort of warm and cool periods. Why did we have an ice age, and why are we not in an ice age right now?
Fundamentally, the way that Earth's climate changes is related to changes in the amount of energy that Earth receives from the sun, which is related to our orbit in space. As Earth moves through space because of the physical interactions with all of the other planets in our solar system and the sun, there are sort of regular cycles of more solar radiation reaching the planet and less solar radiation reaching the planet. And that is one sort of primary driver of why Earth's climate changes. Those changes, though, are very slow. For example, one of the things that drives Earth's climate to change is that our orbit goes from more circular around the sun to more oval-shaped, and that cycle from circular to oval-shaped takes 100,000 years to go through one cycle. It's a very slow process, but it does change the amount of energy that Earth receives. All of the rest of Earth's climate changes are due to what we call feedbacks within the Earth system itself. One really important one is related to the amount of greenhouse gases in our atmosphere. The reason that Earth is habitable is because we have an atmosphere that has greenhouse gases in it. If we didn't have an atmosphere like that, our planet would be much colder than it is today. But as through time, the amount of greenhouse gases like carbon dioxide has fluctuated naturally, and that drives ice ages to come and go. In addition to that, there are other feedback processes related to the ice itself. Like as an ice age begins, as ice sheets start to expand, Earth's surface gets brighter because ice is white and it reflects incoming radiation, which means that as the ice grows bigger, the Earth naturally gets colder. And as Earth gets colder, the ice grows bigger. And so we have these sort of self-reinforcing processes that are occurring on the surface of the planet and in the atmosphere that modulate that incoming solar radiation and result in these big changes in climate that drive ice age cycles.
Mm-hmm. And I'm curious about the development and I think a word in glaciology is nucleation of ice sheets in Antarctica. Mm-hmm. At the same time that Antarctica completely separated itself from the rest of the rest of the continents in the world. So there was the opening of the Drake's Passage, and then that was around the same time that you're saying 34 million years ago, ice sheets started to form. Yeah. So what's the relationship between those two?
Yeah, that's been a topic of research for a while, and I think where things stand now, I mean, this is the really cool thing about research and especially about studying the Earth. There's a lot that we understand, and there's still a lot that we don't, that we have to learn, right? Because the timing of these things is quite closely related. The opening of Drake Passage, when the Antarctic Peninsula separates from the tip of South America, and you get this thermal isolation of Antarctica via the Antarctic Circumpolar Current spinning up, that timing is very close to when Antarctica glaciates. And so it's been suggested that that may have been the trigger for glaciation. There's been quite a bit of modeling work that suggests that opening of the Drake Passage is not enough to glaciate Antarctica, that you have to have falling CO2 in the atmosphere, and that one of the really important processes for ice sheet nucleation, and this is sort of, I don't know if it's counterintuitive or intuitive, but as the ice sheet grows, that positive feedback process related just to insulation, that the albedo goes up and it gets locally colder and the ice can expand. In some senses, the ice sheet itself is responsible for its growth. Modeling studies have shown that the change in CO2 and the growth of the ice sheet itself seem to be the biggest drivers of that rapid expansion of the Antarctic ice sheet 34 million years ago at the Eocene Oligocene transition, and have not yet found a really important role for the ocean circulation. But I think that the jury is still out a little bit. I mean, one of the things that we don't fully understand is what drives the carbon cycle in terms of changes in what drives changes in atmospheric carbon dioxide, where that carbon dioxide goes when it leaves the atmosphere. And the ocean is actually one of the biggest reservoirs of carbon dioxide that we have. It's the second biggest compared to the mantle, right? And so as the Drake Passage opens, it's possible that the models that we've run aren't fully capturing the ways that that opening can actually result in drawdown of CO2 from the atmosphere. So in that way, that process of splitting apart of the continents could be responsible for the drawdown in atmospheric carbon dioxide, which then causes the glaciation. So you sort of have like a link that's not directly driven by that tectonic change, but is certainly, if you trace it back to the beginning, potentially caused by that tectonic change. So it's a mix of things, we think.
Yeah, so it's not direct causation, but it's like a stepping stone effect of different things.
100%. I mean, this is one of the things that I think is fascinating about the Earth. It's one of the most complex systems that we know of. There are so many ways that the atmosphere, the oceans, the ice sheets, the solid Earth itself, a change in one has cascading effects on all of the others that on short time scales and long time scales can cause all of these interesting kind of interactions and feedbacks. And so being an earth scientist, I think, is fundamentally about cultivating an appreciation for this really complex system and trying to trace all of those interactions back to their initial sources.
And then looking at the way that ice sheets are sort of retreating today and comparing that to the past, what makes today's warming and retreating of ice sheets so unnatural compared to the past? I mean, you mentioned that Antarctica didn't always have ice, the Arctic didn't always have ice, and during different points in their history, those ice sheets waxed and waned. So yeah, why is today so different?
That's a very interesting question. So one of the things that is really different about today is how quickly we are putting carbon dioxide into the atmosphere, how quickly atmospheric carbon dioxide is changing, and how quickly global temperature is changing. In terms of what we know about Earth history, we do not have an example of a time when carbon dioxide was this rapidly input to the atmosphere, at least for the last 55 million years. The closest thing we have is 55 million years ago. And we don't really understand what caused. It was a time called the Paleocene-Eocene thermal maximum, when there was some kind of rapid injection of carbon into the atmosphere, and it caused widespread environmental effects and climate warming. Today, we're inputting carbon dioxide into the atmosphere faster than even then, and we don't fully understand what the implications of that are because we have no examples of it from the geologic record. Also, temperature today is changing faster than any time, at least in the last 10,000 years. So this time period when Earth, we call it the Holocene, this interglacial warm period following the last ice age, has been relatively... temperatures have fluctuated, but slowly, if at all. And we don't know of a time when temperature has changed as fast as it is today. In terms of the ice sheets, I think this is an interesting question. Like, are they changing faster than any time in the past? I don't know that we know that they actually are. We know of examples from the geologic record when the ice sheets were bigger than they were today, and they retreated much faster. So there's this interesting time period following the last glacial maximum coming into our present day when global sea level rose at about 4 centimeters per year, which is an order of magnitude higher than it is today. So the ice sheets were retreating really rapidly, driven by this change in climate from an ice age to a warm period. And that's interesting because that rate of sea level rise, I mean, that already we struggle to adapt with 4 millimeters a year. 4 centimeters a year would be really devastating. We know the Earth system is possible of producing that kind of rate of change if forced hard enough. And I use that word, we talk about forcing in climate science, like the driver of a change, right? If we cause temperature to change fast enough, we can cause sea level. We know we can physically cause sea level to change even faster than it is today. But whether or not that will happen in the future remains an open question. And that's why the changes that we're observing in ice sheets today, for example, at Thwaites, where we see indications that there may be positive feedbacks related to retreat already underway, those observations sort of hint at the fact that we might see a type of ice sheet retreat that we actually do know from the geologic past, but what we know about it from the geologic past is that it would be totally devastating to our societies and our infrastructure along the coast and really challenge our ability to adapt to a rapidly changing world. And so I think that's the kind of, there are things about the present moment that are completely unprecedented. But ice sheets, the interesting thing is, we know have actually changed in really profound ways, and that gives us the opportunity to look at the observations of today, which are alarming, but not unprecedented. I think we actually have ways to look to the geologic record for some indication of what the changes might augur.
Yeah, so we can see evidence for the waxing and waning of ice sheets and the pretty rapid waxing and waning, but that wasn't always a good thing. It was probably a pretty bad thing for the plants and animals and the things living on the earth at the time.
Yeah, I mean, I think
it's hard to say without knowledge of paleontology, but
well, yeah, in some ways, it must have been a challenging kind of change. I also think that there is a lot that we might not fully understand about this. Over the last 3 million years, Earth has gone through these ice age cycles where sea level has gone up and down by around 120 meters at its greatest. And clearly, much of the flora and fauna of the world have learned to adapt to that. So I wouldn't say it's a good thing. I wouldn't say it's a bad thing. But it's the way that the Earth has functioned, and the organisms that we live with today, in some ways, have adapted to that kind of environmental change. And so I think that there's ways in which there are ways we might learn from that, questions we might ask about that. How did things adapt to rates of sea level rise that are faster than today? I'm not sure we directly have ways of answering those questions, but I hope that those are the kind of things we might learn more about in the future.
So when we talk about different pieces of evidence for temperature change and CO2 change through time, what is the evidence that we have for that? I know there's benthic evidence, there's atmospheric records from ice that we have. Could you provide me a little detail on that?
Yeah, I would say we have sort of evidence that covers different temporal scales and at different resolutions. You mentioned benthic evidence, so the deep sea, organisms that live near the ocean and preserve ocean chemistry in their shells get preserved in deep sea sediments, and by measuring the chemistry of their shells, we've been able to reconstruct changes in sort of the global climate state, how warm the ocean was and how much ice there was, really over the last 50 million years. We have a really good understanding of that from deep ocean sediments. But because the rate at which that sediment accumulates is relatively slow, we might only have a data point every few thousand years. That's a very low resolution record. On the other hand, if we are willing to look at a shorter period of Earth history, for example, the last 1 million years, which is short to me, I know it's not short to everyone, ice cores preserve information both about temperature, but also directly about what past atmospheric composition was via freezing bubbles of air in the ice itself. And so by measuring both the chemistry of the water and the makeup of the air bubbles that the ice has trapped, we're able to get an understanding of temperature change and changes in atmospheric greenhouse gases from time periods that are really close together, and see how those two things are linked. And what we've learned from that is that over this cycling from ice ages to warm periods in the last 1 million years, there's been a very close link between the concentration of carbon dioxide and the temperature of the Earth. So we can predict from that, even beyond our physical understanding of the way that carbon dioxide functions as a greenhouse gas, which has been known for more than 100 years. We know that within the Earth system itself, as CO2 changes, so too does temperature, which is then allows us to predict what we might expect as we change CO2, even beyond what it was before we started to change it.
So that goes kind of into the idea of combining archival data and physical observations with modeling. And I know that's a theme that you try to reproduce in your research. And so what exactly do you mean by combining, archival data and computer modeling and things like that?
Yeah. So a lot of what we know about Earth history comes from some kind of geologic sample that might be from the ocean, it might be from the edge of the ice sheet, it might be from underneath the ice sheet itself, it might be from within an ice core. And these archives can be really powerful, but they are also spatially limited. We might only have information from a particular core site or a particular location from underneath the ice. And so if we're drawing conclusions about what that observation teaches us, it's difficult to know how widely those conclusions apply. On the other hand, models capture the physical interactions, are built on our understanding of the physics that drives the system, but a model can be used to reproduce almost any reality that you can imagine, right? We have sort of control over what we want Earth's orbit to be, what we assume past atmospheric CO2 was like, and that allows us to reconstruct a whole range of possibilities of what Earth was like. And so, but the benefit of models is that you have this spatially continuous and broad coverage of Earth, and you can understand how the relationship between, for example, the ice sheet changing and how that affects the climate directly around it or even far away from it. That's a kind of understanding that you can't get just from one ice core. And so what I mean when I try to use archival data and modeling together, it's taking a certain set of observations from the geologic record and asking under what kind of assumptions that we put into our model are we able to reproduce those geologic observations? And when we reproduce those geologic observations, what can that teach us about the kind of processes or feedbacks or mechanisms that were occurring when the climate system produced the records that we see.
Mm-hmm. And tell me about isostatic rebound, and how does the accumulation of ice change the elevation of the land?
Okay. Um, yeah. So this is also the kind of one of the things that has drawn me to study ice and fascinated me about ice. Um, I think I first got into ice because I was concerned about the climate crisis, and it was, that movie Chasing Ice. I remember seeing that when I was in college, or in Inconvenient Truth, or all these sort of like images of melting glaciers. It kind of felt like there was this crisis of ice, and it gave me the sense that ice is kind of fragile and endangered. And one of the things that I've come to appreciate and that has really deepened my interest in ice is that while in some ways it is ephemeral and sensitive to changes in its environment, it's also an incredibly powerful force in shaping its environment itself. So I've already kind of mentioned that when I was talking about the way that as the ice sheet grows, that reflects more sunlight and that allows the ice sheet to grow bigger. Another way that the ice affects its environment is that ice is so heavy, it actually deforms the solid earth underneath it. That is a process we often refer to as glacial isostatic adjustment. It's the same kind of principle as when you have an object that floats in water. Because the object is less dense than water, you put it on top of the water and it'll float, and it will float at some depth that's given by Archimedes' principle. The buoyancy force on an object is equal to the weight of the water, the weight of the mass that it displaces, right? We can sort of consider ice to be, it's less dense than the mantle. It sort of floats on the mantle, but because it's so heavy, it actually causes the mantle to sink underneath it. And in general, an ice sheet that is 3 miles thick would cause the depression underneath the thickest part to be about a mile. So the imposition of an ice sheet on Earth's surface can cause really big changes in the elevation of the Earth itself. And that is a process that results in adjustments that we even see around us today. Here in Texas, we don't have a recent history of glaciation, but if you go up to Boston or up to Montreal or even around the edges of the Greenland ice sheet, there are rates of uplift that can be on the order of a centimeter a year, really rapidly uplifting crust. And the reason that's happening is because not so long ago, those areas were actually covered by ice. And when you remove that ice, the mantle is responding, the Earth is rebounding, and that movement is driving the surface of the Earth up. It's pretty incredible to think about the ways that something like the solid Earth, which is, when I think about it, I just think it's this enormous rock that feels sort of like immovable and unchangeable. An ice sheet, which fundamentally is something that, builds up from snow that falls from the atmosphere, can actually impact something that is that big on that scale is pretty incredible to me. And that's one of the things that, really draws me to understanding ice.
Yeah, that's really, really interesting to me as well. I remember when I first looked at like sea level graphs for, like you said, places along or close to Greenland, Norway, sea level was falling. And it, like, from just like normal intuition and what from everyone saying, you're thinking, oh, sea level's rising everywhere and all this. But it's sea level's falling because like the land itself is rising, and it's rising to this day. So, you had ice sheets thousands and thousands, like 20,000 years ago was the last glacial maximum, right? Yeah. And so even after 20,000 years, that land is still rising. Yeah. And so when you depress land down, can you tell me about what happens to the land surrounding it? Because if I'm thinking about, like, I have a water balloon, if I push down on one part of the water balloon, the parts around my fist are going to raise up, right? Is the Earth the same way?
Yeah, you have a very similar kind of response of the solid Earth. The solid Earth we often treat as a viscoelastic material, meaning it has viscous properties. In some ways, it behaves sort of like honey or molasses, and also elastic properties. It has, in some ways, it behaves just like a diving board that you could bend. And it has sort of both of those properties at once. So when you put an ice sheet on it, like a load, you have both this immediate bending effect and also the slow flow of that honey or the molasses below. And when you depress the mantle, for example, at the thickest part of the ice sheet, the material, particularly deeper in the mantle that is flowing away from that depression, ends up accumulating around the edge of the ice sheet, and you get what we call a peripheral forebulge in places. So there are places beyond the ice sheet where you actually have a deflection of the solid Earth upwards when there's an ice sheet imposed on the surface somewhere else. And then when that ice sheet disappears, that forebulge actually collapses, the mantle material flows back. And so there are places where sea level change is happening not just because the ocean level is rising, but also because the ground level is sinking. Places that were on that forebulge, now that the ice is gone, the ground is returning back to its former position at the same time that sea level is rising, and that causes the rate of sea level change locally to be even bigger than for a place where the ground is not rising and the only effect you have is the changing sea level. Sea level is we talk about sea level rise and that being a key challenge of the world that we live in many places around the world. Over the next hundreds of years, we will see sea level rise. It's also true that sea level change is not the same everywhere, and sea level change is the result of many different processes that are driven by the physics of ice sheets and their interactions with the ocean and the land surface. And so understanding sea level change at any given point is not as simple as looking at how quickly the ice sheets globally are melting and making a prediction. Understanding sea level at a given point requires an understanding of the history of how ice has changed on Earth and also what local processes might be going on that are causing the land surface to change and not just the sea surface to change. So although my work mostly sits on the ice sheet side, as we're thinking about our work being applicable to folks that are thinking about sea level change, it really requires a kind of interdisciplinarity and thinking across spatial scales in order to make predictions that are actionable and relevant.
Yeah, I remember when I first was learning about peripheral bulge and GIA and things, it was really astounding to me that the Bahamas, somewhere we think of as so tropical and so far away from any type of ice sheets, in Canada, felt the effects of the Laurentide ice sheet, that huge ice sheet that covered most of Canada. Yeah. It felt those bulging effects, thousands of kilometers away. Yeah. And it really puts in the scale just like how big these ice sheets can get when they do get really big. Yeah. 100%. Is the Laurentide one of the kind of biggest reconstructions that we've been able to produce of ice sheets, and maybe Antarctica as well? But I guess just focusing on North America and Northern Hemisphere for now. Is the Laurentide one of the biggest ice sheets that we know existed?
The Laurentide ice sheet, so this is the name that we give to the ice sheet that covered North America 20,000 years ago at the last glacial maximum, is the Laurentide ice sheet during the last glacial maximum is the biggest ice sheet that we know to have existed during the last 65 million years of Earth history. It's twice as big as the Antarctic is today, and bigger than the Antarctic has ever been. We also think that, there's been many of these ice ages. So the last ice age, the Laurentide was the biggest ice sheet the Earth has ever seen. The ice age before that, it was actually smaller, and there was quite a big ice sheet in Europe. We don't understand why sometimes some ice sheets are bigger than others. These are puzzles about ice ages and how the physical evolution of the Earth happens that really remain to be solved, and that I think are really fascinating. But the Laurentide, this most recent Laurentide ice sheet was spectacularly big.
Yeah, it seems like there's so many positive and negative feedback loops when you think about glaciology, and like even with, let's say, GIA, since we just talked about it. So as you nucleate, as you create an ice sheet, you're building up this huge mound of ice, and so as you move upwards in the atmosphere, the temperature gets colder. That's why Denver is colder than Austin. Yes. And so you're actively increasing or decreasing the surface temperature of that, ice dome that you're slowly turning into an ice sheet over time, but then you're also depressing the ground underneath it. So there's like a force of like negative elevation, and then obviously the positive elevation of building this ice sheet. And that's just like one example of so many other things I can think of that would be positive and negative. And it seems like there's a lot of nonlinearity, and that you could have like a lot of runaway and but also just like stagnation in the building and kind of evolution of ice sheets. Evolution is the right word.
100%. This is what makes the climate system so fascinating, is there is so much nonlinearity that emerges from the interactions of exactly these different processes. And this is where models are so powerful, because these physical processes that you're talking about as being potentially working in different directions, the ice sheet gets thicker, it's going higher up in the atmosphere, it's getting colder, it's also depressing the ground underneath it, which makes it sink. It may also, as the ice grows, start to flow, and the flow of that ice may cause erosion, and that erosion may also change the elevation. There's all of these interconnected processes, and we can represent those in our models and then start to understand which one of those processes might win out over different timescales, and what does that what kind of ice sheet evolution does that result in, and how does that link with changes in the broader climate system. This is, I think, you're hitting the nail on the head of why I think ice sheets are so important for Earth history and for Earth's future, and also why they are really a useful tool for just trying to understand complex systems and learning about interactions between different processes. I think cultivating that kind of understanding is useful regardless of what kind of work you want to do or where you go in the world. And so I think that ice sheets are actually a cool sort of testing ground for challenging ourselves to think about the interrelation and the interconnectedness of different kind of processes at different kinds of scales.
Something fun that I like to think about with ice sheets is that they behave very similarly to the more liquid parts of Earth's mantle. And especially with like there's a ton of really cool things about, I mean, cool really is the right word. There's a ton of really fascinating things about ice sheets, and even like the way that it responds to stress. Because I'm sure like ice has a certain crystalline structure, and its crystals will orient themselves, if they can, in, I don't know the exact direction, but they'll orient themselves in a function of like the maximum stress that's being placed on it. Yeah. And then the orientation of those crystals affects its thermal properties and the way that it flows and different. It's just like so nonlinear, and it's such an amazing system.
Yeah, 100%. The ice crystals will orient themselves orthogonal to the direction of maximum stress. And there's so much active research in understanding what role this plays on changes in ice flow. For example, have a lot of colleagues from time I spent as a PhD student in Copenhagen who are working on understanding it. There's places in Greenland in particular where using radar, we've been able to see through the ice, kind of like an X-ray of the ice sheet, and you can see all of these layers in the ice that correspond to different periods in time. And in many places in Greenland, near the bed of the ice sheet, there are these big disturbances that almost look like a kind of flow instability, like the way you get these little like Kelvin-Helmholtz clouds sometimes in the atmosphere, where you see these little like flow structures. At the bed of the ice sheet, you get these big structures that almost look like
I know what
that.
you're talking about. I read that paper. Yeah.
And there's a big debate about what causes that. Could it be like water that's freezing on from the bed? Or some of my colleagues have been looking at, could it be caused by basically instability at the contact between ice that has different physical properties? Like, are the layers of ice with different crystal orientations actually kind of buckling against one another and causing these like really big flow instabilities? I mean, it's a fascinating, we're talking a lot about scale, and I've been talking a lot about like the scale of the planet. The other thing that is really cool about ice is that there is a micro scale to it, and that ultimately ice sheets are built up of these ice crystals. And you're absolutely right. There are changes at the crystal scale that we think result in changes at the ice sheet scale.
Yeah, I just got done talking to Kiki Schulz, and I just made the connection in my head. It's probably not the same mechanisms at all, because she deals with water and we're thinking about ice. Both are, viscous fluids, ice being nonlinear. I'm not so sure about the viscosity of water. But these like internal turbidity waves, where you get these like areas of high concentration of different elements because there's a lot of turbidity in like this one spot, as you're kind of like shearing water that has different stratigraphic layers, not only vertically but also horizontally towards like a slope. It forms these like kind of mud tongue concentration pockets where you have a lot of turbidity, a lot of sediments flowing, and it looks to the human eye really similar to what you're talking about, with those kind of like bulbous, like high attenuation, almost like cloud looking things in the ice. Her mechanisms are much more like the physics of the different. I should know this because I just talked to her, but it's really hard to understand. But
I'll have to listen to that episode. I look forward to it.
Yeah, it's
no, I mean, this is fascinating. A cool thing about nature too is that there's similarity across different kinds of natural systems. And another example I remember that really sort of activated my imagination when I was first learning about ice sheets is particularly in the Antarctic. We talk about ice streams, which are or glaciers that are embedded within the ice sheet. They're places where the ice is flowing very fast and carrying the ice to the margin where it breaks off. If you follow those ice streams upstream, they become sort of these like tributary systems that look almost like rivers or almost like networks of veins in our body, for small tributaries of flow leading to one really big river of ice. And I just remember thinking, how cool is it that something that's so kind of far away and foreign is actually really familiar in some ways as well.
Yeah. Something I was talking about with a postdoc at UTIG yesterday was how like you have two ice tributaries that meet each other, and then they're like what exactly happens at that margin between the two,
Mm-hmm.
because the stresses on one ice stream
Mm-hmm.
or one ice tributary are going to be
Mm-hmm.
different from another.
Yeah.
And so this is at Thwaites that you're talking about earlier.
Yeah.
Thwaites being this, I don't know if supercritical is the right word, but very very endangered ice sheet that people often attribute to, like, this is the glacier that's going to melt, that's going to cause sea level
The
rise.
Doomsday Glacier.
The Doomsday Glacier is the buzzword that they use for it. But basically, like, you have these two tributaries, and what exactly is going to happen at the margin where those two meet?
Yeah.
And then, like, if you have a different crystal fabric orientation at one because the stresses are different, then there's going to be a ton of shear. And then if there's differential speed between the two, then you're going to get this shear margin, which might create heat. And when you create heat in ice sheets, then you create water. And if there's water at the bottom, then it flows really quickly, which is also something I wanted to ask you about. If you could explain why ice sheets even have water at the bottom, and why does that make them flow so quickly?
Yeah. I want to say that I think this is fascinating, this shear margins where you have a change in ice velocity over a relatively short distance. And so you get a lot of sort of shearing of the ice against itself. I would say the place that we understand this the most, or where we have really deepened our understanding of this, I'm not sure we still understand it, is this place in Northeast Greenland, the Northeast Greenland ice stream. I'm biased because it's a system that I've worked on before, but I find it really interesting. And one of my colleagues had a paper just last year or 2 years ago looking at changes in the fabric, the crystal orientation structure of the ice as the ice moves across the shear margin, and showing that you have this hardening of the ice as you move from outside of the fast flowing region into the fast flowing region, which is so counterintuitive because it's like flowing faster, but through that process, the crystals are aligning in such a way that they actually become harder to deform. So, again, an example of the ways that you have these sort of multiple interacting processes that are going on. And it's cool too, because now for a long time we could only get information about that crystal structure like from physical samples of ice, but there have been recent technological advances, particularly in radar, where we can now, by using a phenomenon called anisotropy, which means that there is a asymmetry in ice crystal if it has a preferred orientation, that anisotropy will lead to a difference in how quickly waves propagate through the ice. And so depending on what direction you look at you collect your radar data, it takes a different amount of time for the radar wave to pass through, and that can actually tell you about this crystal structure of the ice. So I think this is a cool example of the ways that sort of technological advances also allow us to probe new sets of questions and deepen our understanding about some of these interactions that you're talking about. That's because you were talking about shear margins, and that's a fascinating topic. You had asked, why is it that there's water at the base of a glacier or an ice sheet, and why does that cause the ice to flow faster? Was that the question?
Yeah, perfect.
Okay. Okay, the easy one, why is there water at the bed of an ice sheet? Because ice is made of water, and particularly, the bed of an ice sheet is very heterogeneous. Ice, we know it's cold. There's parts of Antarctica where the ice is very cold, minus 20 degrees centigrade all the way through. That ice is not melting. It's just frozen to the rock underneath it, very, very slowly deforming and thinning under the weight of the ice on top. But those are the kind of places where we actively are looking for very, very old ice. So I mentioned before, we know climate history over the last 1 million years from ice cores. It's not everywhere that you can get 1 million year old ice. You need to find a place where there actually isn't water at the base, because if there's water at the base, that means that the ice is melting at the bed. And why does the ice melt at the bed? In places, it's because there's more heat coming up from Earth's surface, the geothermal heat flux. In other places, it's because the temperature of the ice is different. When ice accumulates really quickly, it also carries with it the temperature signature of the atmosphere that it fell in. And so the accumulation rate also impacts how warm the temperature of the ice is all the way throughout. And when the ice is really thick, that also means that it's very insulated from the cold atmosphere at the base, and that can be conditions that, with enough geothermal heat flux, really promote a little bit of melting there at the bed. And so I think the primary reason why there's water at the base of an ice sheet is because somewhere there's melting, somewhere the conditions are such that ice is melting at the very bottom. Then usually that is occurring at rates that are similar to the accumulation rate. So it can be millimeters a year of ice. Probably maybe a centimeter, not much more than that. That water then becomes part of a hydrologic system that we know to be active. That water can move around. The bed of an ice sheet is one of the places on planet Earth that we know the least about, maybe even in our solar system. I don't know, maybe we might know more about the surface of other planetary bodies than we know about the surface of what is beneath the ice itself. We don't know where there's sediment. We don't know exactly where there's water. We don't know where it's just bare rock. We don't know what kind of rock that is. In general, ice deforms because of the force of gravity. One of the things that can resist the flow of ice is the basal shear stress, how strong the bed is and how much it resists the flow of that ice over it. And in general, a wet bed or a bed that has sediment over it is weaker. And so as in all other things being equal, the ice will flow faster over a wet bed or a sediment-covered bed than it would over a hard bed. And that's why where there's water, the ice tends to flow faster. Mm-hmm. It's also more complicated than that because there's a complicated relationship between water at the bed of an ice sheet and how quickly the ice flows. When there's just enough water to lubricate that basal boundary and cause the ice to start slipping, you can get acceleration of the ice as you get more water. But as the amount of water grows, what tends to happen is it tends to flow towards the areas of the lowest pressure, sort of the equivalent of water flowing downhill, but underneath an ice sheet. From high pressure to low pressure. Exactly. And with enough water, the water will start to actually carve out a little channel into the ice and kind of create a conduit for itself. And where you get enough water to create that kind of conduit, that can actually cause all of the water to rush to one place. And that will actually slow the ice sheet back down because the water that was widespread and lubricating everywhere now is able to concentrate in one conduit where it has less of an impact on ice dynamics. And so up to a certain point, what our understanding today is up to a certain point, adding more water to the bed causes the ice to accelerate. Past that point, adding more water to the bed can actually cause the ice to start to decelerate. That is a process that happens seasonally in Greenland. You have like meltwater input to the bed as the summer season starts, and in the beginning of the melt season, you have this speed up, and then as you get more melt, that sort of coalesces and the ice slows down again. But how the movement of water at the bed impacts ice dynamics on longer time scales is still a really active area of research.
And a really hard area of research.
And a really hard area of research. Yeah, there's only we can make a lot of inferences from remotely sensed data. So that can be information about how quickly the ice is flowing from space, and we can use models to assimilate that data and get our best estimate given a certain sliding law of how strong the bed is, but what's causing that. We can look to radar data and try to get some sense of what that basal boundary condition is from, for example, how reflective it is. But we've accessed the bed in Greenland in only a handful of different places. And a lot of times what we learn when we do that is actually our assumptions based on the remotely sensed data were incorrect, that the basal conditions are really different than we imagined. And so the truth is, really, to get information about that, we have to go to the bed. We have to access the bed. And that, as you said, is very difficult to do.
Yeah, that reminds me of the West Antarctic ice sheet divide core that they tried to drill for. And they drilled all the way down, not to the bed, because there was a bunch of water there. So there was a ton of melt, and they just hadn't predicted the melt at all. And I think, to the researchers' credit, I think there were some researchers from UTIG and maybe from other places who were like, hey, there's a lot of heat coming up from the ground. You guys might run into water. But I think there were conflicting arguments, and they wanted this spot. And so, yeah, that just reminds me of what you're talking about there.
Yeah, ice core science is really fascinating, and there's a lot of science questions that go into motivating where we drill an ice core, and there's logistics questions, and there's questions of politics. And an ice core operation it's a huge undertaking. It can take years, multiple field seasons to drill an ice core, and it requires a huge amount of infrastructure to be maintained in an environment that is very difficult to maintain that kind of machinery, right? So it is fascinating, the history of these different places where we have records. And also, to their credit, I mean, the waste divide core, because there's so much melt, that meant that the ice was younger than maybe we thought it would be, but that also means that the record is much higher resolution. We have more ice from the times that we have the ice, and that's pretty cool because we've been able to learn a lot about the connections between the Antarctic ice sheet and the Greenland ice sheet and the rapid climate changes that have happened in the past from having a really high resolution ice core that sort of is a similar resolution to what we get in Greenland, but from the opposite end of the Earth.
Yeah, that's stemming from that idea of ice kind of deforming under its own weight. And so in this case, there was so much melt at the bottom that instead of compressing under its own weight, that ice actually stretched out. And that's why you have that resolution, right?
Yeah. You can think about it like that. Yeah, there's less thinning because there's a greater just downward vertical velocity. The ice is melting at the bottom, so it's constantly sort of creating space for more ice to fill up. Whereas in a place where you're not melting at the bottom, every year you're adding more ice on top, and the layers below all have to thin to make room for that new ice that you're adding. So yeah, you can think about it sort of being this stretched out in time ice core.
Yeah. Another thing that I wanted to ask you about that I still get confused on, and I think you'd be the perfect person to ask, is the timescale and wavelength of these different changes in GIA and then ice sheet growth over time. So a good way to phrase this question would be, so imagine you're accumulating ice at some point, and so we say in Norway that sea level is rising, right? Or sea level is falling, sorry. Just like the microphone. Sea level is falling. Yeah. And so that's because the land itself is rising, but then you start to stack on this weight on top of it again as you nucleate, as you create a new ice sheet, right? And so what happens to that buoyant force that's going up and this kind of like long-term, like almost like wave of buoyancy, like this buoyant force that's going upward while you start to build this ice sheet on top of it? And how does that like affect the actual elevation as a whole?
I mean, that's a question that I've actually thought about writing a proposal to start looking into. I think, and that means that I don't know what the answer is, but I have ideas. I mean, yeah. So this GIA process, there's a response of the solid Earth that is instantaneous when you change the load. That's that elastic part. But then there's this other part of the response that is slow and viscous. And how slow that is depends on the properties of the mantle. So that can be, there's places in Antarctica where we think the mantle properties are such that the response time can be on the order of decades to centuries, super, super fast. As the ice changes, the mantle's just responding really quickly. There's other places where that response takes 10,000 years or longer to fully come back to some kind of equilibrium. And that means that the solid Earth has this sort of memory of past glaciation that is on a timescale that's similar to the nucleation, the waxing and waning of ice sheets.
Yeah, you explained it so much better than I could.
So that means that there's the potential for interaction between these two things. How the solid Earth is changing because of past glaciation may affect the way that the next glaciation happens. That is a question and an idea that I hope to pursue with students in the next couple of years, because I think that it's maybe, I think maybe this is like maybe a theme of the kinds of questions that catch my attention. Is I think it is underappreciated how much of an impact the ice can have on the climate system itself. It's not just responding to the way things are changing. It's really an active player, and not just in terms of what's happening in the atmosphere, also potentially what's happening to the solid Earth, right? Which is like, we talked about that before. I just think because of the scale of things, it's really counterintuitive, and it's really powerful.
Yeah. Is a good analogy, like you're jumping. So a trampoline would be only elastic.
Yes.
But just for simplicity of the analogy, let's say you're jumping on a trampoline at a constant frequency, and then all of a sudden, as you're jumping on the trampoline, your frequency kind of changes, and you like catch the trampoline as it's coming up. And so you almost like cancel out a bit of that force coming up. Or maybe not cancel. When you think of the Earth, maybe I shouldn't say cancel out.
Okay, yeah. Because you're not canceling out in the Earth sense anything, but I appreciate your analogy for this, the idea of kind of resonance. And I think that has actually been explored in thinking about why do we have these ice age cycles that are pretty predictable in terms of their frequency, that there's this sort of regularity to the cycles. And I mentioned before, we have the regularity of cycles of Earth's orbit. That's part of it, but it has also been argued that there's a sort of an aspect of resonance to the way that the climate system is functioning that also is activated by the presence of these ice sheets. The ice sheets kind of enhance the resonance with those orbital frequencies. But the extent to which the solid Earth is also a player in that hasn't been explored, and I think that could be really interesting to look into.
Yeah, and then you get into that idea of like an interdisciplinary science and trying to integrate people who do tomography on the mantle and solid Earth science like that into glaciology, which is just really fascinating. Like it's really cool how we've branched out into all these different disciplines, but as the problem gets more and more complex, and as you develop your understanding of this one discipline, then you start to merge your disciplines together and try to solve like even more complex problems. Because you're right, as you said in the beginning of the show, or of today's episode, the Earth is really complex. It's like one of the most complex things we've observed, right? And it's just really wacky to think about a lot of the time.
Yeah, you seem to have very interdisciplinary interests. What interests you about ice?
About ice? So many things. I think that the modulation of like Earth phenomena. So right now I'm interested in like volcanism in West Antarctica, because you have this big, so for context, there's this huge rift zone in West Antarctica is the section of Antarctica that's in the Western Hemisphere. So that Antarctic Peninsula, if anyone's familiar where Thwaites Glacier is, Mary Bird Land. This is a lot of Antarctica geography jargon, but basically the section of Antarctica that's in the Western Hemisphere, part of that Antarctic crust is separating itself from the rest of Antarctica. And it has to do with like the plate tectonics and the tectonic history. And then Antarctica has a really rich and cool tectonic history because it was once a supercontinent. It was once the center of this supercontinent called Gondwanaland. So Australia and India and Africa and South America were all connected via Antarctica. And then it slowly separated itself over time. And we were talking about earlier the Drake Passage, so that's around 34 million years ago. The Antarctic Peninsula, because of this, I forget the name, it's like the sandwich plate. It's got like it's got a funny name to it, or a funny nickname, but it's basically this microplate that's kind of like barreling itself in between South America and Antarctica, and that's why south of South America and north of Antarctica, in between those two continents, there's like these volcanic islands that are formed through the subduction of that plate under, I think, just like the greater Atlantic oceanic plate. But anyways, so rich tectonic history, and you're basically kind of splitting the crust, the continental crust apart in this area of West Antarctica, and on top of that is upwards of 3 kilometers of ice. And so back to the trampoline analogy, it's like you have this rift system that would already have volcanism. So it's really similar, if anyone's familiar with the rift system in New Mexico in the US. You have really thin crust, and there's actually an ancient supervolcano there in northern New Mexico. It's called the Valles Caldera. It's up near Los Alamos, where like Oppenheimer takes place. Okay. So Los Alamos is like on the foot of that supervolcano. It's this huge, huge volcano. You can so see it from space. Okay. And if you looked at a satellite of New Mexico, it's like this huge crater in like the northern/northwestern part of New Mexico. Okay. Anyway, so when you're splitting the crust apart, you're decreasing the pressure, and so you're inducing melting of this part of the crust, right? Mm-hmm. And so you would already have volcanism, and then there's already this rich tectonic history, so there's probably subduction under Antarctica as well. Mm-hmm. And so when you subduct a plate under another continent, you carry a bunch of water with you if it's covered by ocean. In this case, it was. So you're injecting all this water, which changes the melting point of these rocks, and then you're splitting and thinning the crust, which also induces melting. So you're going to induce all this volcanism, and that's why you see Mount Erebus. Mount Erebus being one of the only volcanoes in the world that has an active lava lake, and it was on a documentary with I forget his name. Really famous like Austrian guy who makes documentaries. It's called Into the Inferno. Highly recommend. It's a really fun documentary. He goes from, I'm going to go on a bit of a tangent, but he goes from like looking at volcanoes and these like French scientists that were a couple that died together.
I saw a documentary about them that was fascinating.
Yeah. I think he talks about them a little bit, and then he talks about like volcanoes in history, and then he like somehow is able to connect that to like North Korean politics at the end of the documentary. It's a wild ride.
What a ride.
But
wow.
It's fun for anity that wants to watch. But anyways,
very interdisciplinary.
Yeah, they did a segment on Mount Erebus, and if you're at McMurdo, which is a station at pretty like decently close to it's actually pretty far from the South Pole. If you're at McMurdo, that's a station in Antarctica, and you can see Mount Erebus, and you can see the smoke coming out of it from McMurdo. And there's a ton of volcanoes on the western side of Antarctica where you have that rift system. So some of the research that I've done myself is on like Mount Takahe, which is this huge like Mount St. Helens. Actually, don't quote me on this because I'm not sure the exact dimensions, but Mount St. Helens, I'll put an asterisk, Mount St. Helens sized volcano.
That order of magnitude.
That has the huge explosive eruptions where you get these ash that blankets all of Antarctica, and then the ash gets incorporated into the ice. Yeah. So you can see these ash layers within the West Antarctic ice sheet, which is really cool. And really all through Antarctica because ash travels thousands of kilometers.
When it erupts, it actually melts through the ice and the ash goes everywhere.
So this volcano is subaerial.
Oh, it is subaerial.
Yeah.
Yeah. Okay.
So this one is so tall, like, Mount St. Helens size, that there's not enough ice to cover it.
That's cool.
And likely when Antarctica, or when the Earth was colder during the last glacial maximum, it was likely subaerial as well.
Yeah.
And so it had to be subglacial at some point. And so,
Why?
Because the volcano, I think, is younger than 34 million years.
Okay.
So it's younger than the presence of ice.
Up. Okay.
Yeah. So I think, actually, don't quote me on that either.
Okay.
That's
fascinating. If
If I'm wrong, I'll listen back to this and I'll put a little text on the video saying how I'm wrong. And all this is in literature if you are interested enough to go read it yourself. But the big question with Mount Takahe was it submarine or subglacial at some point? Because you go into West Antarctic ice sheet stability, because much of that ice sheet is way, way under sea level. Some parts are, I don't know the exact dimensions, but over a kilometer under the sea level. And so basically I have this big dog bowl where all this ice is, and if water seeps into that, then the whole thing collapses, and you end up with this shallow sea. I say shallow, I mean some parts would be a kilometer deep. So you end up with this passageway basically. Yeah. And that volcano at the time probably would have been covered by water or been an island. How did I get here? Oh yeah, so I'm interested in this stuff because going back to the trampoline analogy, imagine you have all these things that I just talked about. So the rich tectonic history, subduction, this rift system, and then you basically just push it up and down with the different loading of that ice sheet over time. Yeah. You're going to induce a lot of really, really weird, cool stuff. Yeah. And a lot of that volcanism is probably subglacial. Yeah. And so you would think, oh, well, if there's a volcano under ice, then it's probably going to melt the whole thing out. Yeah. But there's not a ton of research that's been done, but from what's been done so far, we've been able to kind of conclude that it actually might have a stabilization effect or a slowing down of flow effect, because if you think about the flow and the just dynamics of ice sheets over time and ice streams, it's over really long time scales. Mm-hmm. And so if you have some kind of eruptive event where you have a lot of stuff getting melted, you're going to melt out all of this, so ice is a good insulator, like you said earlier. So you're going to melt out all of that warm stuff on the bottom. And then as ice is flowing through, when you melt the warm stuff on the bottom, cold snow has to take its place. And so you actually, when you melt the warm stuff on the bottom and you have that water that kind of flows into channels and kind of exits the system, then you cool down this entire column of ice, and then it'll actually stick to the bed and stop flowing. More research to be done, of course, but that's our understanding at the moment. Cool. And so that system to me is really cool, and that's why ice is so cool for so many other reasons, the non-linearity of how it flows, its viscosity. Yeah. So if you propagate a thermal wave through ice, so let's say that temperature in Antarctica has warmed up since last glacial maximum, there's going to be a delay between when you feel that at the bottom of the ice sheet and when you feel that at the surface. And that is governed by the diffusivity of ice, among other things like the rate at which, snow kind of falls they call it vertical velocity. Basically, if you had a snow particle and it fell on the ice sheet, how long does it take to work its way down and become ice? But it is largely a function of diffusivity, especially where you have really low vertical velocities. So in places like East Antarctica, where there's not a lot of precipitation, it's like the biggest desert in the world. So it's really cold and there's just a big hunk of ice there. When you warm up the surface temperature, that warm stuff at the top, or the warm temperatures at the top, need time to diffuse through the ice sheet. So that's why if you pour hot water into a cup, it takes time for the whole cup to heat up. Right. And so as you're conducting heat through, that's a function of diffusivity. So this material property, it's like, if you're taking high school physics, it's like the spring constant. It's like a material constant that is basically saying how well does this substance diffuse heat. And thermal conductivity and diffusivity. So diffusivity refers to how quickly it moves through the ice. Conductivity is that's actual how many watts per meter Kelvin can heat travel or energy travel through the ice. But basically, that diffusivity is modulated by temperature as well. Temperature is an independent variable and a dependent variable of diffusivity. Right. So as you propagate a thermal wave through the ice, it's being governed by diffusivity and conductivity, which is also changing with that temperature change that you're inducing. Cool. And there's just so many examples of stuff like that. Yeah. Like you were saying, elevation feedback loops. It really is a really cool system that is honestly kind of fleeting too. We haven't had it for that long if you think about Earth's entire history. Yeah. And we might not have it to the same degree that we do right now in 100 years. Yeah. And when you think about the outer solar system and Europa, there's a bunch of wacky ice stuff going on there. Because imagine everything we're talking about, but instead of the deepest you go is maybe 4 kilometers, now you're talking about 15 across the entire planet. Yeah. And then there being an ice-ocean interface at the bottom of that. Yeah.
Yeah, it's fascinating. The connection between volcanism, I think, is really exciting, and there's some work that's been done in northeast Greenland to look at how the ice sheet coming and going might have thinned the lithosphere there. And there's also a really fascinating paper that was pretty controversial at the time, and I don't know that, and I think more work needs to be done, but suggesting that the mid-ocean ridge in the Atlantic Ocean, where oceanic crust is spreading and being created, that the rate that oceanic crust is being created might be a function of sea level because of the change in pressure. So there's researchers thought they could see the sort of sea level cycle imprinted on the age of the crust at the base of the Atlantic. Which is really exciting, I think, connections between volcanism and ice sheet history, loading, that remain to be explored. So I'm glad that you're digging into those.
Yeah, it's a cool thing to think about with the weights, because it's one of the most rapidly moving ice systems in the world. And it is so endangered as far as the possibility for it to melt, because so much of it is below sea level. So if at the grounding line is basically where the ocean meets ice, and there's usually a lot of floating ice over that. And that floating ice is what you see if you were to drive a boat up to a glacier. So if you were to swim under that, you'd be able to swim for a while. And you guys are getting a robot, and
Yeah.
taking it under
Yeah,
there.
we go to Greenland in a couple of weeks, and we're taking a robot up to some of those exactly interfaces to look at what's going on there.
Yeah, remind me to ask you about that. That's pretty cool. But yeah, essentially, so the grounding line is basically that point under that floating ice where the ocean meets the ice, and it's there's no more ocean. It's just ice after that. And so there's a really, from the grounding line to like the kind of, as you move more towards the interior of Antarctica, there's a really steep gradient of elevation drop off. So if you were to like inject some water into that, then it's kind of a runaway system, because like as grounding line retreats, then more stuff melts, and then as more stuff melts, there's more retreat, and then, you know, possibly, I'm not an expert by any means on ice sheet collapse, but it is it's minimally astonishing that like you could have some kind of runaway system with ice sheet collapse in that specific region, and so much of the ice flow is dictated by the water underneath.
Yeah.
And so much of its thermal properties and things like that. Yeah. And so when you melt stuff off due to volcanic activity, that water has to go somewhere. Yeah. And so its broader implications for that region itself are unclear, and maybe something I'll do, maybe something I won't do, but it's a cool thing to think about.
Yeah, totally.
Let's talk about the rover.
Yeah, so we're headed to Greenland in a couple weeks with one of the themes of this conversation has been all of the different kinds of interactions that ice has with other parts of the Earth system. And we've talked about so many, and here's still yet another one, sediment. One of the ways that we know of past ice sheets is from the sedimentary records that they leave behind. In a lot of North America and Europe, we have these big structures called moraines, which represent the edge of where the ice sheet was at some point in the past. Actually, all of Long Island, like where New York City is the end moraine of the Laurentide ice sheet. The Laurentide ice sheet extended all the way out there and delivered so much sediment that it built up Long Island. These big, as you have just talked about, the geometry of the bed impacts the stability of the ice sheet. And as the ice sheet delivers sediment to its margin, that is then changing the geometry of the bed and potentially having impacts on its stability. But we don't include this process in the models that we run, so we might include the GIA process we've talked about, but we usually assume that any movement of sediment isn't modulating the bed topography enough to make a difference. And yet we know that in some places, the rate of sediment delivery by a glacier to its margin can be orders of magnitude larger than that GIA response. There can be tens of meters per year of sediment that are building up. And so we are curious to observe this process. How is sediment getting delivered to the glacier margin? And then how is it then building up in the fjord? And to use those observations to calibrate a model that will allow us to ask questions like, on what kind of spatial or temporal scales can sediment input potentially be a stabilizing feedback to ice loss? Is that a process that we're missing in models that we use to predict how glaciers might respond in the future? How does sediment flux change in response to changing amounts of water at the bed and other physical processes that are occurring on the glacier? And so we are going up on a research vessel in a couple of weeks to northwest Greenland with a robotic submersible that is designed by a team at Woods Hole Oceanographic Institution that is called the Nereid Under Ice. It's actually been built to work in glaciated environments where there's a lot of ice, and it will allow us to get right up to the margin of the glacier where it's really hard to go in any other kind of vessel because it can be quite dangerous and rapidly changing. You're right next to the ice. And it will allow us to explore that region and take direct measurements of where sediment is coming out, how much sediment is coming out, and also how that relates to how quickly the glacier is moving, how much water we can observe on its surface, to try to piece together a whole picture of what role that sediment might play in the glacier's broader behavior. And in addition to that observation of what's happening today, we will also be collecting sediment cores and seismic data that can help us trace these glaciers and their evolution from the last glacial maximum until the present day. In many of these fjords, we actually see moraines, multiple moraines, and we don't know always how old they are or what their relationship to the ice sheet and climate change was. But by dating them and getting information about their sedimentary structure, we hope to be able to piece together what the role of that moraine was in potentially stabilizing the glacier in the past. And then, because we know that those moraines are no longer occupied, they actually give us multiple sort of examples of sedimentary structures that may have increase the stability of the glacier, but not enough to protect it from retreating. And so through studying both the past and the present, we hope to be able to build a quantitative physical model for what the role of sediment is in glacier stability.
Mm-hmm. That's really, really cool. And I'm really looking forward to what you guys find.
I'm looking forward to the expedition. I think it will be... We're definitely, it's something that hasn't been explored a lot before. And so as always in science, I hope that we're able to confirm some of the hypotheses that we have, while at the same time, I acknowledge that we will likely discover things that we are not expecting to discover, which is always exciting and one of the best things about doing science. Being wrong and being challenged to revisit your understanding of the world to better align with what the observations are and come up with new hypotheses that can deepen our understanding of everything around us.
Yeah, that's going to be really cool. So as we're reaching the end here, yes, I just want to give you some time at the end to talk about anything that you maybe want to talk about but we didn't get to. Or, if you have any upcoming projects you want people to know about, if people want to ask questions, where can they find you?
Thank you. An open-ended question. No, I think this has been really fun. It's fun to have a expansive conversation about ice sheets and particularly their relationship to the rest of the Earth system. I think that's what keeps me doing the kind of work that I do, and it's really fun to get to share that. We have this Greenland project coming up. It's called Terminus. People can read more about that online, and I know that we're sort of currently working on a engagement strategy that means there will be some posts on social media. That's not beyond my capability, but Terminus
that would
project,
be a really cool
UTIG,
documentary for UTIG.
We do have people that are coming to help kind of capture what's happening, and so there will be something related to that. Otherwise, if people want to follow up, they can always send me an email. That's the best way to get in touch with me. I'm just my last name, Keisling at utexas.edu, and happy to talk about ice and its interactions with other parts of the Earth system now, in the past, and into the future.
Awesome. Thank you.
Yeah, thanks for the opportunity. It was really fun chatting with you.
Yeah.